All right, let's take a look at our lesson for today. We're going to be looking at functions and their derivatives, basically the function f. The first derivative and the second derivative are what we're going to be focusing on today. So first, let's look at the relationship between the graphs of f and f prime. So on this first example, we're going to start with the graph. So this is f. Okay, so this is a picture of f. And what we want to do is we want to sketch the first derivative given a picture of the function. Okay, so let's think about that for a second. So how do we read the first derivative off of the position? Okay, so that would be slopes, right? So if we look along this section right here, all these slopes are positive. And we keep looking and we see all of these slopes are positive. So what does it mean when the slopes are positive for the first derivative? That means that f prime is greater than 0 here and here. So we can read the sign of f prime by looking at the slopes, by whether they're positive or negative slopes. So then what we've got right in here, we've got some negative slopes. So what does that mean? That means that f prime is less than 0. Okay, so those are our parameters, our guidelines for drawing f. So what I would like to do is do like a, right underneath it, exactly underneath it, we're going to look at what's going on. So when the first derivative changes from positive to negative, it would have to go through 0, right? So right below here, I'm going to put a point. So it has to go through the x-axis so this is a graph of the first derivative. Okay, so this is f prime of x. All right, so now we've got another change right here. We changed from the first derivative being negative to positive. So let's go down here. And so we would need another 0 right here. Okay, doing good. So let's write, so if the first derivative is positive, that means that f is increasing, so the first derivative is positive. So what does it look like for the first derivative to be positive? Well, it just looks like positive y values. So it's something up here. I mean, I don't know what it looks like. It could be curved. I mean, I don't know. It looks something like this. So there is where f prime is greater than 0 would be above the x-axis. We have another location where f prime is greater than 0. It's over here, the screen section. So I'm going to go ahead and draw that part too. That's where f prime is positive. In other words, has positive y values. All right, so now let's look at the middle section. The middle section is when f prime is less than 0 or negative. That means it needs to be underneath the x-axis, so, somewhere down here. Now, it doesn't really matter how, I mean, I could have drawn it like really narrow like that if I want to. It doesn't really matter because we don't know anymore besides positive and negative. That's all we know is that f prime is positive and negative. And so this would be a representation of what its first derivative might look like. Certainly, it could have different links, or it could go more shallow or more steep, but the idea is there that our first derivative is positive above the x-axis and negative below the x-axis. All right, so that's going from position to first derivative. Now let's do the reverse. Now we have a picture of the first derivative right here. This is our first derivative graph. So we have a picture of that. So let's think about that. So what does the first derivative look like? How does it affect how the position looks? So when the first derivative is below the x-axis, right under here and here, when the first derivative is negative, so let's write that down. So here is where f prime is less than 0, f prime is less than 0. What does that look like on the position? When f prime is less than 0, it says that f is decreasing. So we need to keep that in mind. We're going to draw that in a moment. We need to keep that in mind. So apparently in those two locations, f is decreasing. All right, let's look at the other when f prime is positive is here and here. Okay, f prime is positive, so let's write that in. So this is where f prime is greater than 0. And what does f look like when f prime is greater than 0? Let's see, when f prime is greater than 0, that means that f is increasing. All right, so what we want to do is let's put, let's do a graph right underneath. So we'll line them up. Okay, so let's see what we have. So here, this is a change. It's not a 0 like over on that one. It's just a change. So I just want to put like a little mark right there. So we've got some kind of change going on here. We've got some kind of change going on here and here. So let's think about what the changes are. So when f prime is negative, that means that f is decreasing. So we've got something going on. F is decreasing, decreasing, decreasing until it gets to, right at that little mark right there. It decreases all the way down there because that's what this is saying. F prime is negative, so f is decreasing. Then f prime is positive, so that means f is increasing. It increases all the way to here, this little mark right here. It increases in this section. So let's increase. We're going to increase, increase, increase until we get to there. Okay, good. Again, it could be taller, shorter, I don't know. It just matters that it's increasing. So let's see what's going on here. This is where f prime is negative, so that means f is decreasing, and we want to make that like a curve. So we're decreasing all the way to here. Then we've got f prime being positive, so we are back to increasing. And this would be a graph of f that could correlate with this graph of f prime. Okay, so what that does is that gives us a good picture of what the derivative would look like given the function and what the function would look like given the derivative. So we've looked at both of those scenarios. All right, so let's go to our next example. Our next example is when we're asking for f to be both concave up and decreasing. Let's think about what that means. So concave up, what does concave up look like? That's when f double prime is greater than 0. We know we've talked about that before. Concavity, we can use the second derivative to represent what concavity is, and when second derivative is positive, concave up. Decreasing, let's see, what does that look like? Decreasing, if you recall, that's when f prime is less than 0. So we want, and this is critical right here, we want both of those, not just one or the other, and not just listing the two of them. We want them combined together. We want f to be both concave up and decreasing at the same time. That's our goal, is to figure out when is that going to happen. So what do? Well, we need to find the first and second derivative first. So let's do that. So f prime of x would be, let's see, 2 times 3 is 6x squared plus 8x plus 2. Now that is the first derivative, but to determine increase, decrease, I need to know this. How in the world am I going to know when it's negative? Yes, you're right. I'm going to have to do a sign chart and set the derivative equal to 0. Let's see, I don't really like big numbers, so I'm going to factor out a 2. That would just make me happy, so that's what I'm going to do. And then I'm going to factor. Let's see, so we've got 3x and x. Both sides are positive. So let's see, 3x plus 1x is 4x. Okay, we're good. So then we would set each one equal to 0. So 3x plus each factor equal to 0. So 3x is negative 1, so x is negative 1/3. And I think you can probably do this one in your head. If you set x plus 1 equal to 0, you would get negative 1. So that's what's going on our sign chart. What do we need? We need a negative 1 and a negative 1/3. And of course, we need to put it in, in order. Negative 1, negative 1/3. Now this is a sign chart for f prime. So what does that mean? We basically, how do I check my signs? If you recall, I go back to where I got my signs from. Where did I get -1 and -1/3 from? I got them from, right here. So that's where I'm going to plug my test numbers into to determine the signs. And we've done this before. I'll just remind you, if I put a -2 in here, this factor would be negative and this factor would be negative. Negative times negative is a positive. Okay, and just for time's sake, I'm going to go ahead and fill those in. We're just taking test numbers and subbing them in, and this is what you should get. Okay, so with that, what do we want? We're looking for where f prime is less than 0, so that means f is decreasing. So I'm just going to highlight this little section in here. This is the section that we are interested in. That basically satisfies one of the two criteria. All right, so now let's find the second derivative. So the second derivative would be, what is that, 12x plus 8. So I would set it equal to 0, 12x plus 8, and then I would factor. So what do we have? Those are got a 4. Actually, I don't need to factor. I can just say, just move the 8 over, right? So -8 equals 12x, divide by 12. So x is what? What is that? -2/3. Just reduce that. Take a 4 out of each of those. All right, great. So here's our sign chart for f double prime. Now, where are we going to check these signs? Yep, we're going to check them where we got it from, which is right there. We're going to put them in this to check. So I put in like a 0 in there, and I get, what do I get? So a 0 would be over here. I get a positive. I put a -1 in there, and I get a negative. So those are my signs. So what are we interested in? We're interested in f double prime being greater than 0 or positive. So we're interested in this part right here. That's what we want. That's what we're interested in. Now we need to correlate these two sign charts because we want just the parts that match perfectly, right? Just those. So f prime needs to be between -1 and -1/3, and f double prime needs to be between -2/3 and infinity. So what do we got there? So we want this to be positive, and we want that to be negative. So where would that be? So what we're going to start our word. So we would say f is both, and we just repeat their words back to them. They want concave up and decreasing. F is both concave up and decreasing from -2/3 to -1/3. Okay, that's the section where they overlap. It would kind of be like this if we would want to draw. So from here and here, it's kind of where they overlap. Those two scenarios, concave up and decreasing. And we need to say why, because f double prime is greater than 0 and f prime is less than 0. And that would be our reasoning. All right, so let's keep moving on, continuing to explore the function and its first and second derivative. So this one is number 4. It says a particle is moving along the x-axis, which means it just goes like this, right? Like that all the time, with this function. Find velocity, acceleration, and describe motion. Okay, well, let's find the two equations first. So we've got velocity would just be the derivative. So we do a power rule. So we get what? 1t squared minus 8t plus 12. Acceleration would be, 2t minus 8. Now, in order to describe motion, what are we looking at? So to describe motion, we want to know direction. So are we going left or right? We're on the x-axis, so we're going back and forth, right? Are we going left and right? And we want to determine Like, are we speeding up or slowing down? We're looking at those two scenarios, speeding up or slowing down. Okay, so we need sign charts for that, right? We don't know. So let's set this equal to 0, and then I would factor. So what is that? That is t, the back sign's positive, so they're both negative. What is that, 6 and 2? So my sign chart would have, what, a 2 on it and a 6. And just, I'm just going to go ahead and put the signs in there. I did. Where did I check the signs? Yep, I checked it back in here where I got the numbers from. Negative, positive, negative. Okay, so now let's look at acceleration. We're going to set it equal to 0. So what would t be to make that 0? That would be 4, right? And again, I checked my signs are here. Okay, so let's talk about direction first. So this velocity sign chart indicates direction. So we're going to say particle is moving right. That's when, these are positive right here. That means it's moving right. From negative infinity to 2 and from 6 to infinity, because v is greater than 0. Okay, so we have moving right. And is moving left from 2 to 6 because b is less than 0. Okay, so that's about direction. That's left and right. So check, we got that one. Now let's talk about speeding up and slowing down. So if you recall, speeding up means the signs of acceleration and velocity are the same. Slowing down means the signs are different. So let's look and see what's going on. So from basically negative v to 2, velocity is positive, acceleration is negative. That means we're slowing down. Okay, so we're slowing down from negative infinity to negative 2. And let's look at the next one. So from 2 to 4, those signs are the same, so we're speeding up. So I'm going to start another. So we're speeding up from 2 to 4. Okay, we'll keep moving along from left to right. So now we have, let's see, 4 to infinity for acceleration is positive, but 4 to 6 is negative. So those signs are different, so that belongs in the slowing down. So 4 to 6, and then what do we have? 6 to infinity is speeding up. And so let's say why. So slowing down because acceleration and velocity, we can just put, doesn't matter, velocity and acceleration have different signs. If I could spell signs. And speeding up because velocity and acceleration have different, speeding up is same signs, have same signs. All right, and that's describing motion. So we described direction, left, right, and we also described speeding up and slowing down, which forces us to compare velocity and acceleration. And that is the only way you can tell if we're speeding up, the particle is speeding up or slowing down, is comparing velocity and acceleration, okay? Number 5, we're still contemplating the relationship between f prime, and f double prime. So let's see what they have. So we have values. These are values of f, the position, and they tell us that f prime and f double prime do not change signs. Okay, they don't change signs. Okay, well, that's good to know, just, in case we need to know. All right, so is f just the function? This is just plain old f. Is f increasing or decreasing? Well, how would we know? Well, what we would do is we would look at the y values. So I'm going from a y value of 1 to a y value of 2, 4, 7. Those numbers are getting bigger, right? The numbers are getting bigger. So we would say f is increasing since the y values of f are getting larger. Okay, great. All right, so concavity. How in the world are we going to be able to tell concavity from a position, just a random position numbers? Well, we're going to have to pay attention to these two. F prime and F double prime don't change signs, just so that we know there's no sign changing. So let's think about this. If I look at, if you recall finding average, we're finding average, average f prime. We're finding the average derivative, or average f prime. When we do average, we do, remember, so f of b minus f of a over b minus a. Remember that? I'm just going to do the first one in the formula, then we'll be able to do the others. These are only one space apart. The x's are only one space apart. So that would be what? 2 minus 1 over 1 minus 0, which just gives us, what does that give us? That gives us 1. 2 minus 1 is 1, and 1 over 1 is 1. So that difference, that would be a difference of 1. This is for average first derivative. This difference is what? 2, and this difference is 3. So what is happening to f prime? Is f prime increasing or decreasing? Well, according to this calculation, how we're approximating the average f prime is increasing. F prime is increasing. Now this should make us think about our concavity lesson a little bit ago. Remember, so f prime is increasing. How did that mean? How did that affect concavity? Do you remember that? If f prime is increasing, so f prime is going like this, that means its slopes, which is f double prime, are positive. And what happens when f double prime is positive? Oh, that's right, we are concave up. So we're going to say since f prime is increasing, f is concave up. And that helps us with that one. Okay. So the very last question we're going to do is an FRQ. Oh, I know you're excited about that. They're FRQ. So let's look at this. This was in AP Classroom. So let's pay attention. We've talked about this before. Really important. What kind of graph am I looking at? I'm looking at the graph of F. That is the position. Okay, that is the position. And, it's already, our table is already filled out with, those are all positive. It wants us to fill out all the blanks. So what about f prime? How do we read f prime? Okay, so as I am looking at between -5 and -3, this location right here, f prime is the slopes, along here, and those slopes are positive. So that means that f prime is positive from -5 to -3. Okay, what about these slopes right here? Okay, those slopes are negative. So between -3 and -1, f prime is negative. Okay. Okay, let's keep investigating. From -1 to 2, okay, these slopes are all positive, so that means f prime is positive. And then from 2 to 5, see, those slopes are all negative, so f prime is negative. Okay, so we've talked about that before, how to read f prime off of a graph of f. All right, now let's think about f double prime. So how do we read f double prime off of a graph of f? Well, let's see. So reading f double prime off a graph of f is looking at concavity. I mean, physically looking at it. Remember, for the position, concave up looks like this and concave down looks like that. Right? That's what it looks like. Concave up is when f double prime is greater than 0. Concave down is when f double prime is less than 0. That's what we're looking at. All right, so from -5 to -3, there is no curvature. And I remember we talked about that. Straight lines have no concavity. So that means the second derivative is 0 right there. There is no concavity between -5 and -3 because it's a line. All right, now let's look at this situation from -3 to -1. That is curved up. So that's concave up. So that means f double prime is positive. Okay, from -1 to 2, that is also curved up. So that means that f double prime is positive. From 2 to 5, that's a straight line. It's not curved at all, which means that f double prime would be 0. There is no concavity there. Now they want us to give reasons for our answers. So this is going to take a little bit of writing. I know they're excited about that. Lots of writing. So let's talk about f prime being positive and f prime being negative, how we know. So f prime is positive. And when was it positive? It was positive from -5 to -3. It was positive from -1 to 2. And that's because f, because that's the function, that's the graph we see. We can talk about f because that's the graph we see. Because f is increasing. Okay, so f prime is negative. Let's see, where was that? That was from -3 to -1. And where else? That was from 2 to 5. Because f is decreasing. Okay, easy, not a problem. Now let's talk about f double prime. Okay, so f double prime is 0, and let's see, at, what was it, -5 to -3, and 2 to 5, because f has no concavity. There is no concavity there because it's a straight line. Straight lines don't have any curves. Okay, so now let's talk about f double prime. What else? Oh, it's positive. So f double prime is positive from -3 to -1 and -1 to 2 because, so f double prime is positive because, why? Because f double prime was positive, where are we? Because f is, because we were concave up, because f is concave up. So we looked at it, we physically looked at it to see that f was concave up. Whew, and those are our reasons. All right, let's look at part B. And it's telling us there is no value of x in the open interval -1 to 5 for which, okay, so this, remember, this is mean value theorem right here. Okay, so remember the mean value theorem, f prime of c equals f of b minus f of a over b minus a, where b is 5 and a is -1. Okay, that formula should ring a bell. So they've actually filled out the formula for us. This is the formula. And they're saying that, and remember, that's the conclusion of the mean value theorem. Well, if there isn't any place in the interval where that is true, then why isn't that a problem? Why doesn't that value violate mean value theorem? Well, what do we need to know to do mean value? Remember that, the criteria, what the hypothesis. To use mean value theorem, number 1, f has to be continuous from -1 to 5. Okay, let's look at it. Is f continuous? Yeah, I don't see any holes or anything. Okay, we've met that. Number 2, f has to be, f is differentiable from -1 to 5. Okay, let's look at that. Is it differentiable? Let's see, -1 is right here. No, remember, this is a problem. That corner, if you recall, when functions have a corner, they're non-differentiable. So this is not true. Okay, it is not differentiable between -1 and 5. That's why we basically get a pass. The mean value theorem doesn't have to work because that particular function does not meet all of the criteria. And so that's what we're going to say. We're going to say this, and we always say their words back to it, does not violate, and we can abbreviate mean value theorem since f is not differentiable at x equals 2 because, or we can just say due to corner. So therefore, MVT cannot be applied from -1 to 5. All right, so that's why it's okay. That's why we're good. All right, we got a couple more parts. Let's look at what we got going on here. So part C. All right, find all values. Let's see, what are they saying about G? Let's refocus over here for a moment. They're saying that G prime is F. Well, this is a graph of F, which means it's also a graph of G prime. We're just going to write that there. That is also G prime. They just defined G for us. Okay, got it. We can go with that. So that's also G prime. Okay, and they're asking us here about G. So find all values of x in the open interval at which the graph of G has a point of inflection. Explain your reasoning. Now let's remember here, points of inflection are when concavity changes. When concavity changes. And so that's G prime. We can't visually look at concavity, but if you recall, if G prime changes from increase to decrease or decrease to increase, then we've got an inflection point. That's a change in concavity. So let's see, we've got increase to decrease. We've got something right here. We've got decrease to increase. We've got something right here. We've got increase to decrease, and we've got something right here. So there are 3 locations where that's true. So, and let's write down F equals G prime. I'm just saying you can't write that enough times. You need to be sure to write it in the section that you're using it in, because that's a picture of F. And how can we talk about G if that's F? Well, because F is also G prime, which is why we have to write that down. Okay, so we'll say at x equals -3, -1, and 2, because F equals G prime changes from decrease to increase or increase to decrease, at those locations. At those locations. Okay, great. Oh, we're doing good. We're almost done. Part D. At what value of x does G attain its absolute maximum? There's a key word right here, absolute maximum. Absolute. What do you need to think about when you think about absolute? You need to think about candidates tests. Okay, that's what we think about. What is candidates test? Candidates test involves the endpoints, which we have right here, and critical numbers. And we're talking about G again. Okay, we're talking about G. So G's critical numbers would be when G prime, and that's G prime, is 0 or undefined. Okay, G prime, this picture. This picture is only 0 at -5 and 5, so really we only have 2 candidates. Well, that's not very helpful. And we also don't know the Y values, so we can't actually do a chart, but, and test which one's bigger. So we're going to have to do it a little bit of a different way. So I'm going to say the candidates, I'm still going to name the candidates. The candidates are -5 and 5. And 5 since G has no critical numbers. It basically just has the zeros at -5, and at which they're endpoints as well. So I know that's kind of weird. They're endpoints and they're at 0. But I'm just going to call them endpoints. Okay, candidates are -5 and 5 since G has no critical numbers. I guess we would say other than -5 and 5, where G prime equals 0. Okay, we'll just be specific. All right, so that's all we got. Well, how in the world are we going to tell? What are we going to think about? So if we're starting at -5 and G prime, look at how G prime is. This whole time, G prime is above the x-axis the entire time. What does it mean when G prime is above the x-axis? Well, that means G is increasing. Okay, so since G prime is greater than 0, from -5, from x equals -5 to x equals 5, G is increasing on the entire interval. On the entire, we'll just say on the interval. On the interval. Okay, so if G keeps increasing, big, grow, where's the maximum, the absolute maximum value going to be? Well, there's no choice, right? It has to be at 5. So since G prime is positive from -5 to 5, that means G is increasing on the interval. So the absolute max on the interval would occur at x equals 5, the end point. Oh, those are a lot of words, weren't they? But we need to be very precise in our explanations. All right.